This is a simple example of using Mohr's circle to find Imax and Imin. And of course, we're going to plot the x face. And then from that x face, we're going to find the angle theta p to the nearest Imin or Imax. And this is an example problem from the Hibbeler textbook. It's example problem 10.9. We've actually referred to it a couple times already, but I now actually want to go through it directly, applying the Mohr circle principles that we've learned so far. So this is the complete problem. It's Hibbeler example problem 10.9. It's an S-shaped beam. It's laying on its side. You can tell by looking at it that Ix is probably a little smaller than Iy because more of the area lies along the x-axis. Iy is probably a little bit larger. And most of the area falls on a diagonal from quadrant 2 down to quadrant 4. So you expect Ixy to be negative. And so if you actually do the moment of inertia calculations and the product of inertia calculations, which I will not go through here, you get Ix is 2.9 times 10 to the 9th. You get Iy is 5.6 times 10 to the 9th. And Ixy is negative 3 times 10 to the 9th millimeters to the 4th. So as expected, Ix is smaller, Iy is larger, and Ixy is negative. So we're going to plot Mohr circle. And so what we're going to do is we're going to plot Iavg, which is the average of x and y, and you get 4.25 times 10 to the 9th. The radius, which is Ix minus I over 2 squared, plus Ixy squared, you get 3.29. With those two numbers, and so what I do is I draw the circle first. I just take a blank sheet of paper. I draw the circle. Then I draw the horizontal axis. And then I draw the vertical axis just somewhere to the left of the circle, because the entire circle has to plot on the positive side of the axis. The horizontal axis is moment of inertia. In other words, Ix, Iy, Imax, Imin are all going to plot in this horizontal axis. And all those values have to be positive because they're all the integral of x squared dA or y squared dA because it's square, that square, they're all positive. On the vertical axis is Ixy, it's the product of inertia. And so the top part is positive Ixy, the bottom part is negative Ixy, and exactly along the horizontal axis, Ixy is 0. The middle of Mohr's circle is Iavg. And so we plot our 4.25 there. Our Imax is 4.25 plus the radius, which is 7.54. So that point is 7.54. Our Imin is the center, which is 4.25 minus the radius, minus 3.29, and you get 0.96 is Imin. And so that gives us our circle. It gives us our radius. It gives us our Imax. It gives us our Imin, our Imax and our Imin. So the next step is we need to plot the x face on the circle. And so we come back to the x face, and the x is 2.9, and the point that plots with that is Ixy, which is minus 3. So 2.9 lies on the left-hand edge of the circle, or left-hand side of the circle. So to the left of the center. The center is 4.25, and 2.9 is to the left of that. And if the Ixy was positive, it would plot up. But because the Ixy is negative, it plots down. And so this point right here is our Ixy face. And so the coordinates at that point are 2.9 and minus 3 times 10 to the 9th. So now we want to find the theta p. So that's the angle from our x face to our nearest Imin or Imax. And so our tangent to thetaP equation is equal to negative Ixy divided by, well, I did this different. There's actually two different ways you get this denominator. One way is if you look at this triangle, this leg of the triangle is 4.25 minus 2.9. And this leg of the triangle is Ixy. And so you can actually get it that way, where this first term is an I average, or the center, minus your Ix. You can also use the standard thetaP equation. Well, I don't have it up, but the standard thetaP equation is basically tangent to thetaP is equal to negative Ixy divided by Ix minus Iy divided by 2. And so either way, you can get it from this triangle, or you can get it from the standard equation. Either way, we get 2 thetaP is 65.8 degrees, or thetaP is 32.9 degrees. So it comes out as a positive number. And so well, it's really negative, because we're going from our X face clockwise up to this guy. And that's a negative direction. So really this number should be negative. And it's 65.8 degrees here on Mohr circle, or it's 32.9 degrees on the shape. And you can tell by looking at Mohr circle that takes us to Imin. When you draw these axes on our shape, we know that this axis through the shape is going to be the Imin, because it's passing through the shape. When we go from the x-axis to the right, or clockwise, 32.9 degrees, it's clear that's to the Imin. And so that's what we got here. And then 90 degrees on the shape, or 180 degrees on the circle, is the Iy orientation. And so plotted with this point is Iy and negative Ixy here. And so our Iy is 5.6, and our negative Ixy is a positive 3 up here. So this is a simple example of how to set up Mohr circle, how to find the circle, how to find Imax. I'm sorry, how to find the center, how to find Imax, how to find Imin, how to plot the X face, and how to find the angle from the X face down to the nearest principal, or the nearest, Imax or Imin. Again, when we talk about the principal moments of inertia, we're talking about the max and min, and it's spelled principal PAL. It's not principal PLE, it's principal PAL. They're the principal values, they're the maximum values of the area moment of inertia for that particular shape. And so this is a very convenient kind of problem to use Mohr circle for. Find Ix, find Iy, find Xy, plot the circle, plot the X face, visualize the direction to Imin or Imax. And this is a relatively easy use of Mohr circle. I hope this helps. We'll work more examples.